Hello everybody, I'm Violeta Calian, my co-author is Anton Örn Karlsson and we are from Statistics Iceland. Our work is entitled Measuring and Reporting Uncertainty of AI and Machine Learning Tools in Official Statistics. This is the content of our talk. We will present the goal and the problem, our solution, results, and two illustrative cases, very different, but which we think show exactly what we mean by our solution. The main goal of this work is to stress the fact that the quality and reliability of official statistics can improve and needs to improve by applying up-to-date algorithms and methods, including machine learning and AI algorithms, but doing this in a very rigorous way, detecting, controlling, describing the limitations, and doing all the usual steps that official statistics does in production, evaluating the performance of any method, reporting the uncertainty, the biases, the failures, providing interpretability of results even for black box algorithms, and preserving transparency by using open source code and creating open source code and sharing whenever possible open data. And the solution is obvious, is using standard mathematical statistics methodology. This needs to be applied and adapted sometimes for the advanced tools, methods, and algorithms that I just enumerated. Therefore, one needs to go through some standard steps again, explore the data, and we have a big spectrum of methods to do that. We can fit and train the model or the algorithm used for production, for analysis, for estimation, for inference and prediction. And once that model and algorithm can be fit or trained, one needs to evaluate it, optimize if that is possible by tuning parameters according to some performance metrics, for example, and by calibrating it according to goals. One or the other of these things might become more important depending on the goal of the analysis, as you well know. We want to quantify and report the uncertainty, and this is the emphasis of our talk today, because this is maybe not always the priority of publications, not only for official statistics, but also and even especially sometimes for publications which produce new methods and algorithms of machine learning. And so uncertainty can be due to many causes. As we know, training data variability, model complexity or model fit, distributional differences between the data that we train our model on or algorithm on and the test data. And of course, all possible interactions between this type of uncertainties, as well as biases and failures, which we should be aware of and hunt for even, no matter how clever, new, or complex our tool is, or even more, the more complex the tool is. And we want to describe and interpret the results, as I said, in simple terms. There are nice ways to do that. There are surrogate models, which you can use to map any complicated, complex model, deep learner, neural network, whatever you want, into very simple, with easy interpretation models. One can use feature importance, as we know. We can use conditional posterior distribution checks if one does Bayesian statistics, and we will argue that sometimes this is very, very useful. And therefore, it means that the result of our work or of our research is that these principles can be applied with success, and we will illustrate this in two different cases. Case number one is forecasting population by using Gaussian process priors as components of Bayesian hierarchical generalized additive models. I included here on this slide, as you can see, not only a reference to a paper which we published last year with all the details about the method and the models, but also to GitHub where I share some of the code. And certainly some pictures which show the total population and its evolution in time by the celebrated age pyramid normally shown, but this time with, of course, uncertainty bounds, and also by local projections for 64 municipalities, again with the confidence bands. More exactly, being a Bayesian method, these are credible intervals. And population forecasting, why? Well, on one hand, because it's on huge demand, as you see here, by lots and lots of users. And on the other hand, because of the beautiful mathematical problem and its solutions that we will show in 1 second, in a bit of more detail. The demand comes from national and local administration, come from policymakers, planning infrastructure of all types, future development planning in social sectors in particular, there's big pressure, as you know, health, pensions, education users, and researchers, as well as individual users. And how do we solve this production of population forecast? We do choose a stochastic method. So we are going to model migration, fertility, and mortality, the demographic components of any population development, as functions of multiple attributes, which can be age, time, but not only. They, of course, can be gender, place of birth, education, location in the country, and more. We actually investigated more than those and tested whether they have a significant influence or not on the model. And we want to combine the predictions for these demographic components in a stochastic way according to the standard cohort component, but as I said, in a stochastic version of it. The model has to be able to solve this list of problems, which are usually present for population projections, namely small area, small population issues, rare events or shocks, the way to incorporate expert assumptions as prior information. And for that, as I said, Bayesian methods are particularly suited since we are not working in the classical style of population projections where only expert assumptions were used in order to do the cohort component method. We also need to take into account uncertainty of multiple types, model uncertainty, model parameter or model itself, and errors in the input data, missing data even. The input data errors are well known by the demographers, the deregistration issues, people leaving the country and not going to the registers to announce this. And in one slide, I decided to include everything possible about these very complex models, which we call Bayesian hierarchical generalized additive models, and the implementation into R. So I exemplify here by two very good packages that we have used, the BRMS and the MGCV. And in two words, the way to do this is to model the response. In our case, that is the rates for mortality, fertility, and migration, according to laws, the distribution laws, which depend in turn of some parameters. Those parameters can be distributed according to some other distribution laws, which depend on some other parameters, and so on. This gives a first type of hierarchy in the mathematical way. But on the other hand, there is a different type of hierarchy, and that is in the way that the fact that people share same attributes has an influence on the response, namely on the rates that we can measure and predict at for demography purposes. So there can be attributes which are the same for all individuals. There can be attributes which are the same for a whole group and different between groups. And one can include in this type of models smooth dependencies. It can be dependence of time, there can be dependence of other continuous variable, and those dependencies can be can be different for different categories or groups like this, the ones mentioned before. For example, the dependence on time of a given rate can have a particular shape, which shape can depend in turn on the fact that individuals belong to a group or another, identified by place of birth or by location in the country or by gender, for example, or by education. So these kind of models can incorporate all these demands or all these constraints. And one particular type of smooth dependency that we can include here, which has many advantages, are the Gaussian process priors. And I will come back to this in the next slide with a bit more detail. Of course, I include here a line saying that this particular parameter or function might not be known at all, and then you want just to do a machine learning and not a model depending on parameters or on functions or on a space of functions. And for all this, there are nowadays performance tools working very well and reasonably fast, even in Bayesian, due to both the computer performance and computational tools themselves, which are more and more optimized and better behaving. And I said that a particular type of smoothers were used by us. And here is the connection to what I was mentioning before. Learners, Gaussian processes are somewhere in between modeling and machine learning and keep the advantages of both worlds. They can be defined as distributions over functions. They do no assumptions about the shape of the relation between variables, like a model, a standard parametric model would do, but they can learn from the data the strength of the relation between observations. And this is enough to make them strong tools for interpolation and extrapolation, and that's our most interest in forecasting, therefore. And they can capture, by learning from the data, therefore, while using a rich structure of their covariance function, complex effects like quasi-periodicity, non-stationarity, complex interactions, trend periodicity, seasonality, and autoregressive characters. And that's why we chose to use such smoothers or generalized smoothers, exactly because they are particularly relevant for time series, and not simple time series or one-dimensional time series, but time series, as I explained, depending with responses depending on many, many dimensions. So a bit more complex. And mathematically speaking, they have extremely beautiful properties, like the fact that they are quite general in distributionally and in terms of nonlinearity abilities. The fact that they can be mapped to state space models and the other way around, so there is an equivalence one can prove between at least some type of state space models and Gaussian processes. They can be related to various machine learners, to Kriging, maybe better known for some sector of the statisticians, to Bayesian neural networks, and the newer types of neural networks as well. They include, as particular cases, generalized additive models, and as I said, performing very well for forecasting. And I mentioned here that the smooths in such type of models, in this type of models, they can be also viewed as combination of random and fixed effect, not necessarily the GPs, but the smooths in the slide I just showed before. So that's to establish a connection to more traditional statistics, maybe, and in particular frequentist statistic. So these are the reasons why we chose such tools, which are pretty advanced and not the typical tools for production in official statistics. But on the other hand, they have huge advantages. So they can display and they can give good measures of uncertainty about everything. Uncertainty due to input, uncertainty due to data and to the model. And I illustrate here with just a few pictures, just to show this thing. In figure A, you see here credible intervals relative to fertility rates. And this is part of an analysis of what should be including in the fertility rates modeling and forecasting, trying to discover how many of the attributes that we can have access to have an impact on it, like the type of partnership between spouses, like the type of education of the mothers, like the size of the family. So this is a very good tool and a very good way to quantify these influences and the significance of those influences. We can show how strong the influence of given attributes is on the, for example, mortality rates in a logarithmic scale. I did not include here the uncertainty around the surface because it would just make the figure look much too blurry. But one can look at sections of this. And for example, you can look at the uncertainty about migration. You can tell the general development by age, for example, and its profile peaking at young ages. And as well, we illustrate here with a picture which shows that you can very well have a good control over how well your method's model works. And again, the spectrum of checks that one can do on such model is very large. We just show here posterior checks, but one can do much more than that. Therefore, the case one shows that one can test and validate population projections and demographic components of those population projections in a systematic way. And one can read more details in the paper I mentioned earlier, and I linked here. We can do sensitivity analysis to check the effect of changes in prior distributions. We can also include prior information from the experts via these prior distributions very efficiently. We can test the length of forecasting horizon, which is a feasible one. And we did this. Again, you can see quantitative measures about that in our paper. We can incorporate more and more individual attributes or municipality level attributes. So individual or group level attributes, not necessarily only municipality, but those are most relevant if one looks at local projections. And we can aim for building a unique model. In our case, we did two models, one for total population and one for locals, which relies on the total. The local projections were just modeled as rates out of the total ones, but one can aim at modeling all in one go according to the same principles illustrated above. And even using Markov random fields, for example, for local effects in a more accurate way. One could talk a lot more about this kind of models and analysis, but we have to move on and discuss a bit about a completely different situation and a completely different type of tool or algorithms that one uses in official statistics production. And this is, well, machine learning classifiers for census and survey optimization. So our second case study, again, fully published. So I linked here a paper, which gives, again, much more details that I can include here. So this is a completely done and a lot of work has been incorporated in this case, which contains, of course, the usual steps that I briefly enumerated at the beginning of this talk, meaning one wants to explore, train, test, cross-validate, optimize and calibrate whatever algorithm or learner one decides to use out of a set or ensemble of algorithms, of course. One wants to do performance evaluation according to multiple metrics. This is where the goal of the analysis plays a big role. For census or for survey optimization, one can choose to rank the importance of the metrics in a different way. For the census, for example, one wants to minimize the number of people incorrectly classified as being out of the country while they're in. So this is going to define a particular metric. Or for survey optimization, we showed, at least here in detail in this paper, that this is equivalent to saying that you want to minimize basically the number of errors you do while calling. And that was equivalent to be on the optimum ROC curve. And we showed why. So different goals translate in choosing the different metrics as the most important ones, because one can use many of them for each kind of classifier. And of course, you want to use some interpretability tools as well. So we did exploratory analysis to start with, and maybe a non-standard way, part of the exploration was using some neural